Hello everyone, my name is Jacob. Let's jump right into this problem. Alright, I'm just going to make a force diagram of everything that's happening to this object within the problem. We know that it's on a spring. We're assuming that this is on Earth, so there's gravity pulling down. Here's the spring holding it up. And since this is dynamic, we also know that there's a damping force. And this is just going to be our mg, mass times gravity. This is going to be our ks. It's the spring constant, the firmness of the spring. And this is going to be our beta, our damping force. So from this problem, we can model a situation, or model an equation for the situation. We can say that mx double prime plus beta x prime plus kx is equal to 0. Okay, so now let's list some variables. Our fks is going to model our k. We know that the force is 8 pounds. And our unknown k times, it goes from 4 feet to 8 feet. So that's a total difference of 4 feet. And so our k is equal to 2. Alright, now modeling the beta is nice and easy. Beta is already in there. Now for mass, have this equation. Our force is 8 pounds, once again, equals mass times acceleration due to Earth gravity is 32, and that's just feet, and this isn't meters, this is feet per second squared. And we get our mass is equal to 1/4 slugs. And I could have added units up here, but that's not very important. The importance here is that all of the units coincide with each other. They all agreed with each other. Nothing's in meters. Everything's in feet. Everything's in seconds and pounds and slugs. So here we go. We're going to start plugging into this equation. Square root of 2 2x equals 0. Simplifying, we'll multiply everything by 4. Or, oops. Alright, now the model that we have for solving differential equations like this is the R substitution method. So we're going to say R squared, there's no coefficient here, plus 4 square root of 2R plus 8 equals 0. It's funny, this looks like this won't end up factoring, but it does in the end. We're going to learn that from our quadratic formula, but plugging into our quadratic formula will also be helpful, and we'll get into that in just a second. So we have our R equals negative 4 square root of 2 plus minus 4 square root of 2 squared minus 4 1 8 all over 2 times 1. Alright, and so our R here is going to equal negative, simplifying, separating the terms, 2 square root of 2 plus or minus square root of 32 subtracted by 32 over 2. But this is interesting. This is going to end up equaling 0. And underneath this radical here is our discriminant. And from this discriminant, if we know that underneath the discriminant is equal to 0, that this is going to be critically damped. Okay, so from this little diagram I have over here, we can already tell what this is going to kind of look like. If it's critically damped, it's not even going to have an oscillation. It's just going to go up and come back down. For an underdamped situation, the discriminant would be less than 0. It would just go up and down for a while. Overdamped, it would look kind of like our critically damped, but it wouldn't have as much amplitude. Okay, so that's already an intuition on what's going to happen. Let's get into the specifics. Our R1 is equal to R2 is equal to square root of 2 square root of 2. Alright, so now we can begin our position equation, or equation of motion. X of t, for this example, is equal to e to the r t c1 plus c2t. And our r here, that's just going to be equal to negative 2 square root of 2t. Alright, now we need to solve for these constants. And to do that, we need to use our initial conditions. We have that initially released from the equilibrium position. We know, based on that, x at 0 initial equals 0. It's at equilibrium. And with a downward velocity, it's imparted a downward velocity. So at x prime of 0 equals 4. And it's going to be plus because the convention is that downward motion is going to be plus. Upward motion is going to be minus for this specific instance. Okay, so x of 0 is equal to e. This is just going to be to the 0, which is all just 1. C1 plus C2 times 0 goes to 0. And that equals 0. And we know that equals C1. There's our first constant. X prime at t. Now we got to solve for this bad boy by taking the derivative here. So let's do that in a different color. Since it's the derivative, x prime at t, this guy, we have to use the chain rule. Negative 2 square root of 2, e to the negative 2 square root of 2t, c1, c2t come along for the ride, plus e to the negative 2 square root of 2t. And then only c2 makes it through this time. Simplifying, x prime at t is equal to e to the negative 2 square root of 2 t. And we have negative 2 square root of 2 times c1 plus negative 2 square root of 2 c2t. Oops. Does not look like a t. Plus c2. And this is all going to be equal, so here's, we have our derivative of, so here we have our x prime of t. And now we're going to solve for our c2. So to do that, we're going to actually bring this over. Really handy application. Alright, so I know it's gonna die soon. So x prime at 0 is equal to e to the 0 once again times negative 2 square root of 2. This is gonna be 0 from our last constant, so this goes to 0, this goes to 1. Plus time is 0, so negative 2 square root of 2c2 times 0. That's all going to be 0 again, plus c2, and we know that that is equal to 4, so c2 here is equal to 4. c1 is equal to 0. Now we can make, from this equation, right here, our particular. And we'll do that in a different color. X at time t is equal to e to the negative 2 square root of 2t times c11, which is just 0, and then 4t. Okay, so now we can answer this part of the question. And that ends up checking out. And so we know that the mass attains its extreme displacement when the velocity is equal to 0, because that means it's reached its peak height and it's now starting to turn back around. So x at prime 0 or equals 0 when at max height. So let's set x prime of x equal to 0 and find what we get. E negative 2 square root of 2t, and then we have c1 is just 0, negative 2 square root of 2 times 4t plus 4. Simplifying, setting this equal to 0, we have negative 8 square root of 2 plus 4 equals 0, and then, oh, there's a t there. And then t, the time, would be 1 over 2 square root of 2. Very nice. It's very nice when they come out like that. So we have 1 over 2 square root of 2 seconds, and this is pretty close to 0.3 seconds. So now we're going to solve for the position. Putting into our position, or our equation of motion, x of, oops, we already know our time, 1 over 2 square root of 2 is equal to e to the negative 2 square root of 2 times 1 over 2 square root of 2 times 4 1 over 2 square root of 2. Simplifying, we get e to the negative 1, and then 2 over square root of 2. Simplifying further, we get e to the negative 1, 2 square root of 2 over 2 to rationalize the denominator. And finally, we get this beautiful equation for, or this beautiful answer. It's very simple, very nice looking, and this ends up being pretty close to 0.5 feet. I should probably label that. Alright, so to get an idea of what this would look like, I've prepared a graph. Here's our graph, and it's, if we look at the function, we can see that those agree. It starts from initial, and what's cool about this is that it gets really close, but technically, theoretically, it never approaches 0. It gets close to 0, but it never quite gets there. And more intuitively, it would look like this. If we were to look at it go down and back up again, that's what we're used to thinking about it. But the convention is different. And finally, I have a little cartoon to model the situation. A man that, or a very critical scientist rather, who lives in maple syrup, pushes this weight down. It begins to come back up rather quickly. He's waiting for it to get to or the equilibrium again. He's very critical, so he's going to wait and wait, and he's going to wait a very long time before it ever gets back to that, theoretically. So I hope everyone enjoyed this example. I hope this was helpful, and thank you very much for watching.